Hello, everybody, and welcome back. This is section 7, the theory and generalization. My name is Angela Pasquale. I'm professor at the University of Lorraine in France, and I'm honored to introduce the next speaker. Next speaker is Peng Shan. She's currently a professor at Tsinghua University in Beijing, and she received her PhD from the Université Paris Diderot in 2011 under the direction of Henrique Barcerot. After the graduation, she became a chargée de recherche at French CNRS, and she was affiliated first to the Université de Caen, Normandy, and then to the Université de Paris Sud. She was also CLE Moore instructor at MIT from 2012 to 2013. And in 2017, she joined Tsinghua as a professor. Her research interests lie in geometric representation theory, and more precisely in the study of the representation theory of the algebras, algebras, and quantum groups via geometric and categorical methods. So this afternoon, she will talk on geometrical realization on centers. Thank you very much, Peng.
So it's my great honor to speak here. Today, I want to talk about geometrical realization of centers. So I confess I hesitated if I should survey the work in the past or talk about what I'm most excited at the moment and look into the future. And then I decided I should look into the future and tell you what I'm interested in now and some perspective of it. So here is the plan of the talk. After an introduction, I will talk about affine Springer fibers, and then we'll relate their cohomology to the center of quantum groups. And then I will give some perspectives and other examples. Okay, so as we know, the center of a ring is the subring consisting of elements in this ring A, which commute with everybody else. And we can define in a similar way the center of a category, which is just the endomorphism of the identity function. So in particular, if you have a category with just one object, then its endomorphism is an algebra. And if you take this definition and compute its center, it's precisely the center of the category. The center of an algebra is an important invariant. And for example, every semi-simple algebra is Morita equivalent to center. For example, when we study finite groups, representation of them over compact fields, the study of their center is a very important part for characterizing representations of this group. And also the center is invariant under Morita and derived equivalent. And on the geometric side, now if we take a compact algebraic variety and just take its classical topology, and then we can take its singular cohomology for this topological space. So in my talk, I will take the coefficients of the cohomology to be in C. And for all the examples we consider, the odd degree of the cohomology will vanish. So if you take a cohomology ring and equip it with a cut product, it's super commutative. But if the odd parts vanish, then it is a commutative ring. And the cohomology is the important invariant of a topological space. And as we'll see later, it also in some situations provides important representation. And basically, the theme we're interested in is to give some relationship between centers and cohomology. And especially in this talk, I will focus on the center of small quantum groups and cohomologies of affine Springer fibers. So let me start by introducing affine Springer fibers. So I will start with the finite case. So let G be a semi-simple algebraic group over compact numbers, and we fix T to be a maximal torus inside it. And then we have this Springer resolution. So which goes from the cotangent of the flag variety to the nilpotent cone. So the flag variety consists of all the Borel subalgebras in G. And if you take its cotangent, a vector in a fiber at the point Borel can be identified with an element in its radical. So we can describe a point in T star B as a pair E of a nilpotent element and a Borel such that E belongs to E. And this map is just sending such a pair to E. And the Springer fiber are just simply the fiber of this morphism. So to give you some examples, for example, if we take E to be 0, then it's inside all the Borels. So the fiber is just the whole flag variety. And if you take a regular nilpotent element, then there's a unique Borel contained in it. So the fiber is just a point. And the other fibers will vary between these two situations. So for example, an important example is the subregular element. And in this case, the fiber is the union of one. So Springer fibers are projective varieties, which may be singular. And in 1976, Springer constructed a very interesting while group action on the cohomology of these fibers. And moreover, he showed that all the irreducible representation of W can be realized in such spaces. So this now goes under the name Springer correspondence, and it's an important example of realizing representations by geometric methods. And then in 88, Lustig extended his action to an action of the bigger algebras graded upon height. Okay, and now I want to talk about the relationship between cohomology of Springer fiber and center. So for the Lie algebra G, the category O is a category of highest weight modules over which the Borel acts locally finitely. And it's an important object in the study of the G. So Zogel proved if we take the principal block of this category O and take its center, then as a ring, it is isomorphic to the cohomology of the flag variety. So this is a first instance where you see the center of a category is isomorphic to cohomology of the variety. And this was one of the starting points for the study of causal duality on category O. It's an important subject. And then later, Kovanov conjectured that if you take a parabolic subcategory O, then its center should be isomorphic to cohomology of some Springer fibers. So this conjecture was in type A, and it was proved by Brandon and Stockholm independently around 2008. And so they show that the center of this parabolic category O, which is subcategories where parabolic acts locally finitely, is isomorphic to the cohomology of Springer fiber for the potent element, which is regular in Olivier. And then such patterns extend also to singular blocks where you need to replace Springer fibers by so-called Spatech-time varieties. And the Springer action we discussed just now can also be realized on the center using some trace operators associated to translation complex. So now let's go to the affine case. And in this case, we consider the loop group. And so G double parenthesis Z. And here we have the affine analog of flag variety, which is the loop group quotient by a Uehara subgroup. And in this situation, if you take a so-called topological nilpotent element gamma, so here it's with respect to the dyadic topology on this Lie algebra, and the affine Springer fiber can be defined in similar way as before. So this is the definition of this variety, and it was first studied by Kashtan Lustig around 1988. And so this affine Springer fiber can be infinite dimensional in general, because the affine flag manifold is infinite dimensional. But if you assume gamma is a regular semi-simple element, then this variety is locally a finite dimensional, and moreover, it's equidimensional, meaning its irreducible components all have the same dimension. And then Lustig constructed the analog of Springer correspondence in the Springer action in this situation, where he showed you have action of the affine while group on the top cohomology of this affine Springer fiber. And then there are several works concerning the study of graded double affine height algebras actions on the cohomology of this affine Springer fibers. So this was done by Vesro for K theory, and then Varnilo Vesro the cohomology, and then later Oblom-Coffin also did some instructions related to this. And moreover, affine Springer fiber is related to orbital integrals in automorphic forms. And also, there is an ongoing, very exciting project about developing a affine Springer theory in terms of perverse sheets on the loop algebra by Peng Shan and Warshak. So for us, we will be interested in two very important family of affine Springer fibers. So one is called elliptic fiber. So this is a certain family of elliptic elements. The importance of them is that when gamma is elliptic, then the affine Springer fiber is really a finite dimensional algebraic variety. And for example, here I give an example of elliptic element, which is gamma prime u, and you just take the sum of all the Cholet generators ei, and then plus the theta's height root, so f theta times z to the power of u. So when u and the Cox-Miller number are co-prime to each other, this is an elliptic element. And since the variety is finite dimensional, then its cohomology is also finite dimensional. And this provides finite dimensional representations of the affine algebra. So the finite dimensional representations of gamma are rare, and so it's important to realize them. And then for certain finite dimensional representations, Cherenik showed that there's actually a Verlinde algebra structure on these spaces. And in particular, you have a projective action of the group, the modular group SL2. Okay, and then yeah, maybe just in type A, if you take the special case where U is H plus 1, then this cohomology is actually the diagonal co-invariant ring. And this is an important object in combinatorics, and it's related to Catalan numbers, McDonald polynomials. Okay, and another fiber we'll be interested in is called stick fibers. And in this case, I just take a simple example where S is a regular element in the original torus C, and you multiply it by Z, and then becomes topologically nilpotent. And so this is, if you take this element, its Springer fiber has particular nice structure. So for example, it has an affine paving. And also, since T is the maximal torus, it's normalized gamma, so it's centralized gamma. So it also acts on this fiber. And for this action, this fiber is actually a so-called GKM space. Means that it has isolated fixed points and well, some additional condition on the one-dimensional orbits, making the equivariant cohomology of this space very can be nicely described in explicit combinatorial terms. And so, as we said, we have a fine wild group action on the cohomology of this Springer fiber. This is given by this Springer action. And for this particular fiber, there is also a symmetry on the variety itself, which gives this co-character lattice action XRT, and which extends to an action of the extended wild group. And so these two actions, so this extended group wild group action commutes with the fine wild group action. So in the next part of the talk, we will focus on this split fiber. And so we relate its cohomology to the center of small quantum groups. But as we said, in the original category O case, if you take the principal blocks, you have Springer fibers. But if you take singular blocks, you need to take some split-time variety. So for our situation, if we want to have all these varieties together, then there's a nice way to organize them. And so this is our setting. So what we're going to take is we'll fix L to be an odd integer bigger than the Cox-Miller number, and then co-prime to the determinant of the Carnot matrix. And then we fix zeta to be an L root of unity. And we consider the so-called affine Grassmannian is this loop group quotient by the positive loop groups. So it's the curve here. And on it, we have an action of the torus, which is just multiplication on the left. And we also have a C star action, which just rotate, it acts on the variable Z, send Z to T. And so, and we take a similar fiber as before. So we take S to be regular in T, and we take gamma L to be S tensor Z to the power of L. And we consider this affine Springer fiber now inside this affine graph onion. And the remarkable thing is that if you now take the zeta fit point in this fiber. So zeta is a complex number. I view it as inside the C star rotation, and I can take its fixed point. And its fixed point actually decomposed into a disjoint union of smaller statistician varieties. So this is the meaning of this decomposition, and we'll see later this is related to the block decomposition on the same. Okay, so here are two pieces of important notation. I will denote lambda check the co-character lattice of P, and WLX is the L extended Well group. And the cohomology, again, as before, it has GKM presentation so that we can describe the equivariant cohomology. And then we have the action of this extended Well group on the top. Okay, so this is about the Springer fiber part. Now let's go to the quantum groups. So for the quantum groups, I will take G check to be a connected, simply connected algebraic group, which is long-length dual to G. And then I take P check to be the dual torus. And so note that lambda check was the co-characters for the torus before, and now it becomes the character of the dual torus. And the quantum group is the quantization of the enveloping algebra of G check. So it's a CQ algebra generated by Chevalier generators and subject to valorization. What is important to us is that they have two integral forms. One is defined by the function TOFT. So this is a C bracket Q plus minus 1 set algebra just generated by its original generators. And there's the elliptic form where you add more generator in it. So you add also the divided powers of your generators. So the definition of divided powers is written here. And then so since you have more generators in the elliptic quantum group, so you have a natural map, the embedding from the Castro-Concini quantum group to the elliptic one. But now these two are defined over this ring, so you can specialize Q to any non-zero complex number. So in particular, I can specialize Q to the roots of unity or zeta before, and then I get a map from these quantum groups at roots of unity. Note that they're different. And when you specialize Q to zeta, this map is no more injective because, for example, EI to the power of L will be the L factorial times the EI divided power L, but L factorial when you take Q L to Q of unity to 0. So the small quantum group is defined as the image of this map. And just three important properties of this small quantum group. The first is the finite dimensional Hopf algebra. And second, you can also, like if you describe the kernel of phi zeta, it is an ideal generated by the L powers of the generator root vectors and KL lambda minus. And finally, we have a Frobenius map from Lustig's quantum group to the enveloping algebra of G check, whose kernel is actually generated by the generators of this small quantum group. Okay, and in particular, so if you consider the Hopf joint action of Lustig quantum group on itself, so you can prove it preserves the subalgebra to the small quantum group, and it also preserves its center. But on its center, the small quantum group, the adjoint action is trivial. And so the action factorized through the kernel of the Frobenius and induces an action of the enveloping algebra. And you can integrate this action to an action of the group. So therefore, we get an action of the long and few group on the center of the small quantum group. And its invariant part can be described as the center of the Lucid quantum group intersection with the small quantum. Okay, so here's the first result, which relates cohomology of center. So so this one and all I'm going to talk following is joint work with David Pavnikov, Jose de Alvarez, and Eric Castro. So it's a very recent work this year. And so we first constructed an algebra homomorphism from the cohomology of this zeta fixed point in the Affine-Grassmannian to the center of Lucid quantum group. And we show that its image lands in the G-invariant part of the small quantum group. And let me just say a word about the construction of this map. So first, we use an algebraic description of the cohomology of this zeta fixed points in the Affine-Grassmannian as a Riesz algebra for this ring, which the functions on the dual torus quotient by W with respect to the ideal defined as follows. So I take the map from P check over W to itself, which just raise an element to its L power. And then I take the fiber of this map at 1. I take the scheme theoretic fiber. And this is a fine scheme, so there's a fine ideal for it. And this is my I. And then I take the Riesz algebra for this algebra. And this is isomorphic to the cohomology of the Affine-Grassmannian. And you can view this as a subalgebra inside CT check with H bar plus minus 1 generated by the algebra itself and the ideal. So the next step is that we use the Harshanda map, which gives you a map from this algebra to the center of the Lucid quantum group, completed with parameters. And then you can show it extends to the ideal I, and therefore it extends to this Riesz algebra. So this gives you a deformed version of this map, and you specialize your parameter H bar, and this gives you the map in the theorem. And then you need to show you have generators on the cohomology of Affine-Grassmannian. You need to show lengths in the small one. Okay, and now I want to talk about relation with the Springer fiber. And for this purpose, I need a deformation of the small quantum group. So recall that the small quantum group is the quotient of the Konchini-Katz quantum group by the ideal generated by these elements. Now I can take a commutative ring, which is just the completion of function on the dual torus as 1. And this is isomorphic to the completion of this Lie algebra at 0. And so we can identify it with equivariant cohomology of the point completed. And then the deformed algebra is just I take the quotient of U, dk, zeta tensor with S, and I still quotient out the F to the power of L and E to the power of L, but I will keep the case. So the case goes into this deformation ring. And then I consider the lambda graded modules over this deformed algebra. So this category was studied by Anderson, Jens, and Zogel in 1994. And they proved that this category is causal, but there was no identification of causal dual for this category. And the second result I want to present is that there is an S algebra isomorphism between the center of this deformed modules over this deformed small quantum group and the cohomology of this affine Springer fiber. So this was the zeta fixed point in the affine Springer fiber we discussed before. And so here we get an isomorphism of rings. And moreover, if you specialize the equivariant parameter, it will correspond to killing the deformation on the small quantum group. And we can induce a ring embedding from the cohomology of Springer fiber to the center of the non-deformed small quantum group. And then, as I said, on the left, you have this lattice action, L lambda check. And if you take its invariant part, it will goes into the T invariant part of this center for the small quantum group. So here, remember I explained you have G check action on the center, and T check is a subgroup, so you can consider it there. Okay, so then the third result is the compatibility between the two morphisms I explained. So in the first theorem, I explained a map from the cohomology of the Affine Grassmannian to the center, to the G invariant part of the center. And in the second part, I explained you have a map from the L lambda check invariant part to the T invariant part of the center. And then we know that the affine Springer fiber is a closed subscheme inside the affine Grassmannian. So we can take the pullback, and on cohomology, it induces a map from here to there should be a gamma L here, WLX invariant part. So this is by construction, it will land inside this WL extended affine wild group invariant part. And so this is this map on the left, and on the right, since T check is a subgroup of G check, so you have a natural embedding of the G check invariance inside the T check invariance. And the statement is that all these maps fits into a commutative diagram. And in particular, from this diagram, you can see that since the image of the left arrow lands inside the W invariant part, and so you deduce an embedding of this WLX invariant part inside the G invariant part of it. And so we conjecture, so we prove this is an embedding, and we actually conjecture this is an isomorphism. And right. So why this is useful? Because so the center, as we'll see also later, that the center of a small quantum group is an important object of study, but it's quite complicated, and you want to understand its dimension. But despite the effort of many people, it's still unknown until now. But with this, we can give some estimation of the dimension of the center. So this is the also part of our work, and also independently proved by Hermel, and Lechosa. So if we take H to be the Coxeter number of G and R's rank, and E1, ER the exponents of the wild group, then we have an explicit formula for the dimension of this cohomology part. So this left hand side. So we have we can use geometric methods to compute its dimension. And if the conjecture holds, then this would give a formula for the dimension of the G invariant part of the center. And in type A, there is an additional conjecture, which is this. Actually, in type A, this G action is trivial. So in type A, you do expect to get the whole center. And this formula was conjectured by Igor Frankel, Lechosa, and Snew. Okay. Right. And also, I want to mention that the proof for this formula, like our proof, relies on a comparison between this cohomology space and the cohomology of some elliptic fiber, which is better understood. And this formula comes from the computation of dimensions for that elliptic fiber. All right. So some remarks. So first of all, on the cohomology side, I had this decomposition of this zeta fixed point into different connected components. And this matches the decomposition of the center of small quantum groups into different blocks. And second, if we consider the regular block that corresponds to taking the full affine flag variety, the component which is a full affine flag variety, and then we have an action of the affine wild group on this space. This action can also be realized on the center using trace operators. And finally, so the connection we discussed between the center and the cohomology of affine Springer fiber actually suggests some causal duality between the microlocal shifts on this affine Springer fibers and the category of modules over small quantum groups. And this causal duality will be established in upcoming work of Daisy Kavenkov, Wazeda Alvarez, Max Ring, and Yun. So finally, let me mention some perspectives and other examples. So first of all, I want to say that all the results I explained have some modular analogs. So meaning that now let's take K to be a algebraic closed field of positive characteristics. And to simplify, let's assume P is large enough. And now we can take beta equals to 1. So if you think of it as an element in K, then it generates a group of order P. So we'll take L to be equals to P. And then in this situation, of course, on the cohomology side, you will need a K vector space. So you want to take the varieties. If you define over C, the coefficient of your cohomology will be in this positive characteristic. And on the representation side, you take the long-line steel group to be defined over K. And then if you take beta to be 1, the Concini-Katz quantum group will become just the enveloping algebra of the dually algebra. And the Lustig quantum group becomes the algebra of distributions on G check. So in characteristic 0, these two coincide, but in characteristic P, they do not coincide. And then the small quantum group is replaced by the so-called restricted enveloping algebra. And its representation is equivalent to what's so-called the kernel of the Frobenius map on G. And then with these replacements, one can try to establish all the theorem, all the results I have explained so far. So this is a work in progress. But the characteristic P situation has some new phenomenon, because in characteristic 0, the Frobenius map goes from Lustig quantum group to the enveloping algebra, and then you stop there. But in characteristic P, the Frobenius map goes from G check to itself. So you can iterate this map and take the kernel of its R power. So this gives you some new groups, and you can ask whether their center has some interpretation in terms of cohomology of some variety. So a second perspective I want to mention is the relation to 3D topological quantum field theory. So around 1991, Rashtikin and Torayev constructed for any modular Hopf algebra a 3D TQFT, which is a functor which goes from the cobordism category for three-dimensional varieties to the category of vector spaces. And in particular, this functor associates a torus. If they take the image of the torus under this functor, the vector space is actually the center of this Hopf algebra. And with this TQFT, it has a natural action of the mapping class group on this space. And in the case of torus, it gives you a projected SL2Z action on it. So some version of non-semi-simple extension of theory can be applied to the small quantum group. And in particular, you would expect to obtain in this way an action of SL2Z on the center of the small quantum group. And as I explained, so our theorem gives you embedding from the W invariant parts of this cohomology of Affine Springer fibers to the center of the small quantum group. And we showed that the vector space is isomorphic to cohomology of some elliptic fibers. And this realized certain finite dimensional representation of double affine Heike algebra. And for certain kinds of finite dimensional representations, Cherenik proved Cherenik constructed a Verlinde algebra structure. So in particular, you have an SL2Z action. And the natural question to ask is, do these actions, do they compatible to each other? And the second question is, here we took the image of the invariant associated torus, but if you replace the torus by a genus G surface, and then what this theory gives you on the right-hand side is the following. So you take the home space from the trivial representation of U zeta to G copies of U zeta, but with the diagonal adjoint action. And you take the home space. If G equals to 1, and then this is precisely the adjoint invariant in U zeta, so it's precisely the center. And now well, for general G, you have such a space, and the question is, does it have some geometric realization? All right, and then a third perspective I want, for related work I want to mention is about admissible representations and elliptic fiber. So as we know, in 1994, Kashan-Lustig established a tensor equivalence between representation of Lustig quantum groups and affine the algebras at negative level. And then Finkelberg established a similar equivalence for positive level. But this is all at integer levels for affine the algebras. And then around 89, Katz-Wakimoto studied a particular family of representations of affine the algebras at so-called admissible level. And the interest of these representations is that, so the admissible, if you fix the level to be admissible, then the representation category is semi-simple. But the characters of the simple modules has some modular invariance. And the interest for such representation actually comes from the study of classifying which kind of representation characters have modular invariance. And we will consider a particular case where it's called boundary admissible level. So it's kappa equals to h over u minus h. H is the Fokker number, and u is any integer which is co-primed h. And remember, I introduced you this elliptic fiber for this gamma u prime in the first part of the talk, and it has a C star action with isolated fixed points. And with Xiedan and Yanwen-Bin, we proved the following theorem. So if G is a simply Lie algebra and assume kappa to be boundary admissible of this form, then there's a natural isomorphism between the center of admissible module category and the cohomology of the fixed points in this elliptic fiber. And moreover, since on admissible representations have modular invariance, you also have projective representation of SL2Z on the characters. And we show that this coincides with the SL2Z action on the cohomology of elliptic fiber when you view it as a finite dimensional representation of Taha. So you use it defined by Chernik. And they coincide, so the two spaces have the same Verlinda algebra structure. And this result actually holds more generally. It holds also for representation for W algebras, and then you need to replace Springer fibers by citation varieties. And then we also have some match between admissible weights and fixed points in the Springer fibers at non-admissible levels. Okay, yeah, to end, I just want to mention that this connection between center and cohomology go beyond Springer fibers. So here is an example of such a result. So if you take Q to be a quiver, then there's an Kazmudi algebra associated. And to such data, people have studied like analog of Springer resolution. It's provided by certain symplectic varieties called Nakajima quiver varieties. And on cohomology, you have an action of the current Lie algebra for this Lie algebra G. So it's the action of GQZ. So this was constructed by Varaniolo. And so this action now is the analog of Springer action before. And there's also a family of graded algebras called cyclotomic quiver hexaalgebras, which appears in the program of categorization for G representations. And so there's, if we consider G of type ABE, then there's an isomorphism between the center of quiver hexaalgebras and the cohomology of transitional quiver. And we also establish an analogous isomorphism for Jordan quiver, where you, on the right-hand side, you will have some physical space appears, and on the left-hand side, you have center of some degenerate upon hexaalgebras, which can be computed explicitly. So that gives an example where you can use such isomorphisms to actually compute cohomology of some space. So it goes the other way around. Use centers to compute cohomology. Okay, and I hope in the future we'll see more connections of the center and cohomology. That's all for my talk.
So thank you. I would like just to inform you if you have a question to address to Professor Peng Shan, please use the channel provided, and there is a link in the page on the Discord of ICM. And this was the last talk for section 7 today. Thank you and goodbye.